Back to my YouTube channel. We're still under strength of material N6. So here we'll be dealing with this typical question. It's a bending and deflection. It's a combination of the two. All right, if given that says a solid steel shaft with an outer diameter of 100 millimeter is simple. Check the weight is simple supported. It is simple what is simply supported there. So the steel shaft, we have the steel shaft is round like this. Obviously, it is simply supported. It is simply supported. That means at the end we'll have our reaction. It's simply supported like that. All right. Simply supported at its end. The density of the steel shaft, we've given what the density. That means if we have a density, that means we'll consider what the mass of this shaft. All right. If you consider the mass of this shaft, it's like now you have UTL. It's the same as like take it as if like you have a UTL, because when you consider what the density, when you consider density, you can think of what of UTL. All right. When you consider what the density there of the shaft, we took it. All right. So now it says we're given what the maximum allowable bending stress. Maximum allowable bending what? Bending stress in the shaft is given is 65 megapascal. The shaft is supported with a point load of what? We've given a point load there of 200 kilonewton at mid span. That means at the middle, exactly at the middle. Take E young modulus of the steel as 200 gigapascal. All right, that means here at the middle, exactly there at the middle, we'll have our point load. We'll have what? The point load that will be acting there. You can say W, but it's a point load. It's acting in the middle. Take a note. It's acting where in the middle, which is good. So, given 3.1 says calculate the suitable allowable length of the steel shaft. 6 marks. So we've given what? The maximum bending moment. We know when you have given the shaft, how do we determine the bending moment? That bending moment, how do we determine the bending moment? This maximum bending moment, we know because we've given the shaft, remember, is simply supported, right? Remember, you'll consider what for the point load. Remember, for the point load, you'll have your the bending moment is WL divided by what? By 4. Is for only what? For point load. For the point load. But now, since, remember, they said we have given what a density. In other words, we'll take the mass of this into consideration. We'll take the mass of this because when you, if you've given this now, remember, we can take the weight of the shaft itself, whereby we know the weight of the shaft itself. We'll know that density. Remember, the weight is like it's mass multiplied by what? By gravity. But what about the mass? There, if we've given the mass, we know the mass is equals to what? So you come from, you know, your fluids. For we know how you know that density is given by what? Since you've given mass divided by what? By volume. Here we have mass. So if you make mass the subject, you'll have density multiplied by what? By the volume there. You'll multiply that by the volume. That is what you'll have there. So this, the weight of the shaft will be what? You substitute that will be density multiplied by volume multiplied by what? By the gravity. But what is volume? The volume is given by length, by area multiplied by what? By length. It's area multiplied by the length. All right, so this is what we'll have now. Will be area multiplied by the length, since that it is volume. So you let me cancel that volume there. So in actual fact, that means we'll have density multiplied by gravity multiplied by volume, area multiplied by what? By the length of the shaft. So this is how you determine the weight considering what? The density. So that will be the weight of what? Of the distributed. The one of the distributed, not of the point load, of the distributed. The all right, because of the shaft. So since we will have this, it's a simply supported, you have to add what? Depending due to what? To UTL, we know that will be what? WL squared divided by what? By 8, when we are considering what? The UTL, the weight of this, of the shaft. So this is a formula you're supposed to go about. Then we have to determine what? The length with. So by the way, since we know that we can use that formula, then we'll determine our length, because we have to determine the length there. After all, are we together? So let's do. So now we've broken everything apart. Can 3.1 can have our 3.1 there. So we know that we'll have that there on the top. We'll have our beam, right? We know that we will have our bending moment, we said, should be equals to weight all divided by 4. Now we together is what we have said. We divide this by what? By 4. All right. That is what we have spoken about. Is what it is what we have spoken about this about, right? All right. That is what we have. Okay. Plus, we said due to UTL, you consider the UTL is in it. We divide this by 8. Then we square this considering the UTL. So this is the formula you're supposed to use. All right. We know that is what you're supposed to use. So this is a bending moment, but if given what? The maximum, or we should calculate what the maximum bending moment. So if you've given, check the stress is equals to the M divided by, obviously we want this maximum point because we don't have directly that we've given this. It's a maximum allowable bending stress. All right, this is the bending stress in the shaft. No, okay, bending stress. Are we together? So we have to determine that bending stress. We have the bending stress there. We're given the stress. Sorry about that. It's not the bending moment. You're given the bending stress, but as we want the length, if we want the length, we must have the bending moment. Then, if we can have that bending moment, will be good. We have the bending stress, but if we can have the bending moment, if we can have this, then we can determine the length there. So we want the bending moment, we've given the stress, we know this will be, this formula, right? So we want that guy there. That is what we want. If you make that guy the subject of the formula, you will multiply then divide by L will be, will simply equals to stress multiplied by our y, by divide by y. Oh, this formula, sorry, this is not a, I know why the stress cannot fall. Remember that the formula, it is bending moment multiplied by y divided by moment of inertia. Yeah, this is it. So I want this guy, I'll simply make that guy the subject. I'll multiply there and divide by this guy. Alright, so this is what we'll have there anyway. So Are we given the stress here? Are we given I? So that it's a moment of inertia. We know that is given. They said it's a solid shaft, like it's F the circle, it has the diameter. So this will be what, when you're considering this cross section is the circle, why it will be pi over 64. Do not forget that. Multiply by what? By diameter raised to the power of what? Of 4. This is 4, right? This is what we have. All right. So we can determine our I then. Let's get the I, our moment of inertia, pi over 64. What is the diameter? We go to the statement. The outer diameter given there to be 100 millimeter. So in other words, the same as like we have 0.1. It's the same as what is 0.1 raised to the power 4. Alright, then what is I? Punching this, we should obtain the value of I. Are we together there? I will give me 4,909 times 10 to the power of minus 6 is measured in meter fourth there, raised to the power 4. Alright, we have I. We are done with what? With I. So the stress we are given, the bending stress, it's a bending stress actually. You can use B there, it's a bending stress, we know. We've given now the bending stress. What about this guy? Wiper. Wiper is simply just height divided by 2. It's a height divided by 2. Alright, so if you've given a shaft, here it's a steel shaft. Check where is the height. Height is this, is from there at the top until like this. We call this is a height. This is a length. That is not a height, this is a length. So the height will be the same as diameter. So actually this will simply cause what? Diameter divided by what? By 2, because the height will be the same as what is diameter. So that is what we'll obtain then. So we'll have our wiper, the diameter there, it was 100, whereby with 0.1 divided by 2, right? This will be watt. So 0.1 divided by 2 will be simply have that. We'll obtain that. That it's our wipe, that will be 0.05, right? Right. So we have this now, so we can determine the bending moment. So bending moment we know will be the bending stress multiplied by I moment of inertia divided by y. So the stress we are given there on the statement, it is 65 megapascal. So we have 65 times 10 to the power of 6. Our I is this one. We've obtained 4,909 909 times 10 to the power of minus 6 divided by I, it was 0.05. So we can simply punch this. We'll have our bending moment, maximum bending moment. So the bending moment that we'll obtain must be 6,382. Obviously it's measured in Newton meter. We have this now. Okay, we have that here. We have, so can apply our formula. You can use the formula that we know, that will be WL4 plus the distributed load, WL squared divided by 8. Remember, we've given this, isn't it? Simply support that. This is our length there. So this is for the point load. We know that we'll have this guy, we have this guy. We have calculated the point load we have, but the distributed load we don't have. But we said that the distributed load there, we said will be what? Density, isn't it? It will be our density multiplied by gravity multiplied by the area by the length. So the density we are given there, as you can see, is 700 and what there, 7,800. We are given that 7,800. Gravity is 9,81. What about the area? Remember, it's a circle, will be pi over 4. The diameter is 0,1. We square this, we multiply this by the length. What is the length of the shaft? The length. We don't know actually. We want to calculate what the length, the allowable length here. We don't know that length because actually what is the it's what we're supposed to determine. So will be multiplied by what? By the length. We don't know the length anyways. So we don't know. Either way, we took it. We don't know that length. But now since we don't have that length, since remember it's for the distributed, we must, this is calculated per Newton, is Newton per meter. Remember the distributed load is Newton per meter. So if you don't know this, just put 1. We'll take this as per what? Per meter. Replace it with 1. It's not necessarily, yeah, just put 1. You just put 1 there. Put 1 will be 1 multiplied by 1. We took it. If you multiply that by 1, all of that, when you punch it, you'll have 600,971. Obvious is Newton per. Will you have used 1? Will be what? Per meter, per length, per. The length there is what? Per meter. So it's fine. We have this now. So we can have the, what we have that is 6,382. Then here will be equals to the other guy. We know the point load, we do know it's here, is given to us there. The point load is 2 kilonewton. 2 kilonewton is like 2 times 10 to the power of what? Of positive 3. The length we don't know, divide by 4 plus the guy 600,971 length squared, we don't know, divide this by what? By 8. So this is what we have now. This is what we have so far. So we have this side 63 is not comma, that's 60. It shouldn't, is not a comma. So I don't know why I've this is not a comma. This is not a comma there. That is not a comma. It's simply just that. All right. Now we took care. That is what we'll have. Is not a comma one. So we have 66, 63, 8, 2, okay, here, the answer, if it was in kilonewton or was not, if it's in kilonewton, it was correct, will be comma if it is kilonewton meter, but let me not use that kilonewton meter. It is fine. Let me just write Newton meter. If I write Newton meter, so I will stick with this one. Let me not put a comma because must be in kilonewton. That means the final answer that we're supposed to obtain, but because the length I cannot be, so let me use it without comma there. I will use 6382. All right, it is fine. The one that I wrote before, it is fine. It was kilonewton, isn't it? But let me just use it in Newton meter. It was in kilonewton meter. So let me use this. It's fine like that. So I have 6382 must be equal. Just punch this. There on your nice calculator, will have 500 length plus punching this again. Together, you have 75,121 L squared. So we have this now. So here it's a matter of we want L. You must realize this is a quadratic. It's a quadratic formula. We'll use the quadratic. Taking this, I will take this to the other side. You must understand will be minus 6382. This is a quadratic, guys. Quadratic. I hope you know quadratic formula. For quadratic, we want the length. We'll use the quadratic minus b plus or minus square root of b squared minus 4ac divided by 2a. Quadratic formula. L will be equals to minus, what is b? You know b will be this. It's a quadratic, isn't it? That is b 500 plus or minus the square root plus or minus the square root of b, which is 500 squared minus 4. What is a? Here it's a 75,121. C is this guy. Because it's negative, we include the negative. 6382 comma, yeah. So we divide all of these by 2. Our a is this 75,121. Then we'll obtain the length. If you punch that quadratic, you know, right? So we obtain this to be 6,472 meter. Do not use the negative one. The negative, do not use it. Use the one which is positive. The length is always positive. So this is the one that will obtain. This is our length there. All right. That is our length. So 3.2, the maximum deflection of the shaft. The maximum what? Deflection of the shaft. The maximum deflection of the shaft. So one thing you must realize again is that we want the deflection of the shaft. All right. The maximum deflection of what? Of the shaft. Maximum deflection of the shaft. So you must remember this is simply supported. All right, it's just simply supported. Here we have it distributed. So you have two things. Here we have what? The point load. Or let me try and use a different color there. So you will see this is a point load in the middle. So we must consider, obviously we have to have the maximum deflection simply supported, isn't it? So the deflection, the maximum one, we know the deflection will be what? Will be the deflection due to what? Due to the point load I'll just say W plus the deflection due to what? UDL. Remember, this is going to do like that. It's going to deflect like that. It's going to bend like that. Alright, it's going to bend like that. It's a combination that our beam will bend like this there when you apply that. So we'll have the bending. So our deflection there, simply just the total, actually simply just the total, but yeah, that is our deflection there. So this is our maximum deflection. That is what we're supposed to have. So anyways, let's have this deflection due to the point load. What is that? The formula. And the one due to the point load, and the one due to the UDL. So let's, you know, the formulas. We have WL raised to the power of 3 divided by 48, right? Then multiplied by Young modulus of elasticity, multiplied by which is this our moment of inertia. We'll have plus, we'll consider now the UDL. We'll have W L raised to the power of what now will be 4 divided by 384, right, multiplied by EI. So that is what we'll have the total there all together. So we can substitute now what we know. The point load we did determine. We know what is the weight of the point load. It was 2 kilonewton, which is times 10 to the power of 3. The length is the one that we've just obtained. Now we did calculate the length, which is 6 comma there, 6,472 there. So we cubed there because we've cubed, divided by 48. We have 48. Moment of inertia is the one that we have determined before. We did calculate it before. We substitute our moment of inertia whereby it was 4,909 times 10 power of minus 6. Then let's check Young modulus of elasticity. Are we given Young modulus of elasticity? 200 gigapascal. Take Young modulus 200 gigapascal. So it'll be 200 times 10 to the power of minus 9. So plus, now plus the one of the distributed, it was what? 600,971. The length is the one that we've calculated, 6,472. Now we'll raise this to the power of 4. Divide this by 384. Young modulus is 200 times 10 to the power of 9. Young modulus times 10 to the power of 9. Then multiply by I is the one, is the same there, 4,909 times 10 to the minus 6. Alright, so this is what we should obtain so far. That is what we're supposed to obtain. What will be this deflection? Will have 25,489. The final answer, I'll just write this in millimeter, but you're supposed to obtain your answer in meter, then you multiply by 1000, will be in millimeter. So that is this. There, we have obtained that. Right, the deflection. So 3.3 says determine the magnitude, the magnitude of the force in a prop that will reduce the deflection. In question 3.22, that will reduce to 11 millimeter when is placed in the center of the beam. When is placed in the center of the beam, that will reduce the prop. The prop is acting upwards. Okay? I hope you know the prop is acting upwards. The prop is acting upwards. I've discussed about the prop. Let's say here it's our beam. Remember, we'll have our, this thing is the way it's distributed. So the prop will acting there. The setting descent will acting like this. We'll try to reduce this. Will act. Remember, this beam will go like this, and then this one will try to act upwards. You're supposed to subtract. I said when they're acting in the opposite direction, you simply just subtract. You will subtract them. What do you mean by subtracting? I mean that your prop, your deflection of the deflection due to the prop one, you must know that you must subtract. The deflection will be the deflection, remember, of the one that you've just calculated now, 489, minus the one that you've given, which is 11 there. All right, we have 14,489 millimeter, because it was 11. They said you will reduce this what? So just remember, reduce the deflection. Reduce deflection by 11. When you reduce, you subtract. Remember, you are reducing. Yeah. All right, then let's determine the prop. The exact prop. They said they want what? The prop or the what? Okay, we've determined the prop. Determine then the place center there. We want to determine the magnitude of the force that they have placed it in center of the prop. Okay, where we know now the prop is equal itself. The formula of this prop is point load, the one that is acting below, the point load that is acting at the bottom. If we the one that is acting like that, anything that is acting upwards is a prop. We call it the prop there. The one is acting there in the middle will be multiplied by L raised to the power of 3 divided by 48 EI, like this. All right, now we have this now there. It will be 14,4. We have that. It's 14,489 will be times 10 to the power of minus 3, because I just won't use it in meter. P, the length is the one that we've obtained. It was 6,472. We did calculate this. Length 48. The modulus is 200 times 10 to the power of minus 9 since it's giga. The moment of inertia does not change, because we're still using the same shaft anyways. So now we can determine our P. So you simply punch this. After you've punched that, you divide it. The value that you'll obtain here, divide it here, divide on the both side. Therefore you'll get your P to be equals to what? Point low, your this thing will get to be 2,519 kilonewton. For obtain that, 19 kilonewton. So this is what you'll obtain so far. So thank you for watching. May you kindly subscribe to my YouTube channel. If you've not subscribed, become the part of the family and click the notification button so that you'll be notified whenever I post a new video.